Hi, welcome to this video on reactions that are occurring in aqueous solutions. So aqueous just means in water, so we want to remember that. We learned that earlier. So aqueous solutions are when we put an ionic compound into water so that it can react. You can do this also with molecular compounds as well, so it doesn't have to be just ionic, but typically when you're doing a reaction in an aqueous solution, usually you have some sort of solid. Well, what we know is a solid is not going to easily react with another reactant because it prefers itself. So it's not going to, we can't get it to interact. So what we typically do is take the solid and we add it to water, so then it will dissolve, assuming it dissolves. So in our previous notes, right? So I'm going to put a little asterisk there. In our previous notes, we talked about solubility rules, how there are some compounds that do not dissolve well in water and some that do. So if something is very soluble, it will make an aqueous solution or dissolve into its ions in solution. So I have a good little picture over here on the right for you to see. I'm going to make it a little bigger so you can see it a little better. Oops. My bad on that. Let me shift this over. Okay, so in this picture, what you can see happening is that I've got this barium chloride solid, right? And so when it's in the solid phase, it actually just settles to the bottom, right? So but when I add it to water, when it dissolves, what it does is it takes the BaCl2, right, and it splits it. So the water molecules, and I'll show you a video of this in class, actually come in and attack it, and they pull these away. And so it pulls away the barium ion and separates it. And then it comes in, and water comes in, and it pulls away, and it separates your chlorines into individual pieces. So it completely breaks all the ions apart. So for example, in this formula, there were 1 barium and 2 chlorines, so I have 3 things floating around in my solution for every one of my barium chlorides. So I have 3 ions. But it basically frees up those ions, and so now those ions are free to go and have other ionic reactions with other things. But it doesn't change the charge or the oxidation number at all. All it does is just break them apart so then they can interact. So the barium positive could interact with another negative ion that maybe isn't chlorine if it likes that better. Okay? So that's really what's happening here. So when we make it into an aqueous solution, we're just freeing those ions and making them freely movable so that they can interact with each other. So that's what your solubility rules are. When something is aqueous, that's what happens. When it is not aqueous or insoluble, it doesn't do that. It won't break apart. It just stays together and sits on the bottom. So that's what happens with something that doesn't like water. All right, complete balanced reaction. So we've talked about this for a double replacement in my last video. It shows the ionic compounds that are written as formulas. So I've got silver nitrate and potassium chloride. So this is a double replacement. And so what we're going to do is switch our metals. So we're going to end up with K. Oh, it would actually help if I picked the pen. All right. So we're going to have K, and then with NO3. And the charge on that is a +1 and a -1. And we're going to have silver with the chlorine, which again, silver's +1, chlorine's -1. So this whole reaction is balanced because everything's ones or coefficients of ones, right? So this would be my complete balanced equation. So then what we would do is we would use our solubility rules to look to see what's aqueous and what's not. So if you get out your solubility rules from the notes, those are pretty comprehensive. But I did write some down here. So the next thing we would do after we write our complete balanced equation is we want to look at what's really happening in our reaction. So we write a complete ionic equation. So the complete ionic equation is meant to show us what everything actually looks like in the solution, even though we can't visibly see it. So that means that we're going to show all of our ionic compounds dissociated or separated into their ions as long as they are dissolved in water, okay? If they are not aqueous or soluble, then we would keep them together, okay? We're going to use our solubility rules to identify the aqueous compounds. And then anything that is a solid, a liquid, or a gas does not dissociate. So those have no ions. So no separate ions, I guess is a better way to say it, because you can have an ionic compound that's insoluble, okay? But basically those are considered insoluble things. So we're not going to separate those. The only substances that should be written in an ionic equation are the soluble salts. These strong acids, if you see those, strong acids always break apart, and strong bases, which are pretty much anything that's a hydroxide that's a group 1. One of the solubility rules I had told you guys in class, but I also would like to point out, is anything that's an alkali metal is always very, very soluble. All right, so if I take my complete equation that I had up here and I bring it down here, basically what I'm going to do is I'm going to look at my solubility rules. So in the solubility rules, if we look at nitrates, I'm going to do this in yellow so you can see it a little better. If we look at nitrates on our solubility rules, the nitrate is always soluble. So that's going to be aqueous. And again, potassium chloride, group 1 metals, the potassium is always aqueous. So anything that's in group 1. So we're starting with those two aqueous solutions, and we look at our products. Nitrates are always soluble, so that's aqueous, meaning that those ions are still floating around in the solution. The AgCl, though, chlorine, when I look at chlorine, is soluble unless it's with silver, mercury, or lead. This is an exception. That's a solid or an insoluble precipitate. So that means in this reaction, the precipitation reaction was actually making silver chloride. So that would stay together and settle to the bottom as a solid. So what does that really look like in my solution? It's going to look very similar to this little beaker or test tube that you see over here on the right. Is you're going to see that you're going to have all your ions mixed up, right? Because we started with the two aqueous solutions initially. We put them together, and as we put them together, we see that the little AgCl down here clumps up because it's a solid or insoluble. Those ions find each other and then they stick together and make solid. These other ions are still floating around. So we still see the K plus and the NO3 minus ions floating around. Okay? So when we write a complete ionic equation, we're really just showing what does it look like in those two solutions. Ions are separated as ions. So for example, with my reactants, I start with all ions. So I've got a single silver ion. We have to put charges for ions. So Ag plus. And I've got the single nitrate, NO3 minus for nitrates. And so notice I'm separating each ion with a plus because now they're floating around in the water. It's the only time you can ever write them as an ion is when they're in water. And then I have K plus separated from Cl minus. So that's what's going on in this first test tube over here. All my stuff is separated into ions because they're all aqueous. On the product side, my KNO3 is still separated. K plus and NO3 minus never come together. They never find anything. But AgCl found each other. So AgCl, my solid, is insoluble. We have to write it together as a neutral compound because it's settling on the bottom. So our insoluble compound stays together as one whole. So this would be called a complete ionic equation. It's showing what it looks like initially as reactants when everything's in ion form. And then it shows what's still in ion form in the products, but also what made the precipitate or the insoluble compound. So it could also make a gas or it can make a liquid, something like that. So then from here, we can single out what we call spectator ions. Spectator ions are the ions that actually aren't doing anything. So when I actually look at my reaction here, right, this precipitation reaction is really making silver chloride. So that means silver and chlorine are making that, right? So my spectator ions, in this case, are the ones that don't do anything. So my spectators in this case would be nitrate and potassium, because when I look at them in the equation, I have a -1 and it's still nitrate -1 floating around. I have K plus 1, and I still have K plus 1 floating around. So they didn't change. They didn't do anything in the reaction. So that's what we're really looking at. Anything that's still floating around is considered a spectator ion. Okay? We're making the silver chloride. So your net ionic equation just gets rid of spectators. So we would remove those. So my net ionic equation is the silver ion that's plus 1 and the chlorine ion, right, making the silver chloride molecule. So what this purpose of the net ionic equation is to show us what's really involved in the precipitation reaction or the reaction we're talking about. So these are only the particles involved. So a net ionic is really important because it helps us kind of narrow down, and we can ignore the other stuff. It doesn't mean that the other stuff isn't there, but we know that it's not really changing anything. It's going to be the same at the beginning and the same at the end. Okay? So let me do another example for you. All right? So in this, it's giving us the full equation. We do need to balance it, though. So we're going to balance. To balance this, I need a, let's see, 2 in front of the HCl, and that should fix it up. Okay, so then from there, we're going to go look at our solubility rules. We already practiced this, right? We're going to look for chlorine, chlorine soluble, and this is not an exception, so that's aqueous. The ZnS, when we look at our solubility rules, we're going to see that sulfur is insoluble unless it's with ammonium, alkali metals, calcium, strontium, or barium. So it doesn't fit one of the exceptions. So in this case, actually, this is going to be insoluble or a solid, okay? So really this reaction is not going to happen, but we're going to talk about that in a minute. So we're going to assume it does, but really normally you would write no reaction on that. So that was probably my mistake on this one when I was setting this up. We're making H2S gas, okay? And then ZnCl2. Oh, actually, I'm just kidding. So this is a double replacement reaction. It's just not a precipitation reaction. We're making a gas instead. So it doesn't matter that we started with aqueous and a solid. And then ZnCl2, the chlorines are always soluble unless there was silver, mercury, or lead. So that's aqueous. So when we do, that's our complete balanced equation. So then what we're going to do is we're going to write our, so the first thing from there is to write the complete ionic equation. Anything that's aqueous breaks apart. So if we see the AQ or soluble, it breaks apart into the ions. You want to pay attention to your quantity. So this is going to break into H plus and Cl minus, but we want to pay attention to this, to the coefficient. It's 2 of each of those, okay? And my ZnS is not going to break apart, stays together because it's a solid or insoluble. And we're going to make H2S. So H2S gas is also considered insoluble. It's just not a precipitate. So we keep that together. So you keep gases, solids, and liquids always together. And then again, we see AQ, so we're going to break that apart. So that's going to be broken into zinc ions. And we talked about this in redox reactions. When we're talking about ions, we can't use the subscript. We put a coefficient of 2 for those Cl minus ions on there. So this would be my entire reaction shown as a complete ionic equation, right? The whole ionic equation. So now what we're going to do is we're going to keep anything that is a solid, liquid, or a gas because those cannot be eliminated from the reaction. So that means that if I have it on one side or the other, I need to make sure I'm keeping it. So I'm going to have to keep zinc over here, and I'm going to have to keep hydrogen over here. So my spectators are going to be the chlorine. The chlorine's not really involved in either part of my reaction. So we would get rid of that. So the second part for your net reaction is getting rid of the spectator. So we're going to eliminate the chlorines out, and we would write what's left. So 2 hydrogens are reacting with the zinc sulfide solid, and when it does that, it's producing H2S gas, okay, and Zn plus 2 ions. So we would see those ions be floating around. So this is not a precipitation reaction. We made a gas, not a solid, okay? But it is a double replacement reaction, and you can write net ionic equations for anything when aqueous solutions are involved. So this next one is a single replacement example. So with the single replacement example, first thing I want to do, I'm going to go back and do the same colors. Okay, so we want to make sure it's balanced. I'm going to need 2 NAs and two NABRs and 2 NaCls to make that balanced. Then I'm going to check my solubility. Well, obviously, chlorine is a gas at room temperature, right? Sodium bromide is an ionic compound, so we need to decide, is this aqueous or not? So NABR, when we look at our solubility rules, bromine is always soluble, and it's with an alkali metal, so definitely soluble. Bromine is a liquid at room temperature by itself. Sodium chloride is also soluble or aqueous. So then we're going to go back in and we're going to write the complete ionic equation based on everything we have. Remember, gases, solids, and liquids stay together. So Cl2 stays together. I'm going to break apart the aqueous. So 2 sodium ions, which are +1, and 2 bromine ions, which are -1. I would like to remind you, if you do not put charges on the ions, it's not correct. I will not give you points if you do not put charges on your ions. That's going to make Br2 liquid. And the sodium chloride, again, is ions, so 2 sodium plus ions and 2 Cl minus ions. So when we look back at what's left, right? Well, we know that the chlorine and the bromine are the main things, right? So we need to keep the bromine ions, we need to keep the chlorine ions. The sodium is not changing. Those are my spectators. So we're going to eliminate them, and we're going to write the net ionic equation. So the net would be what's left. Cl2 reacts with 2 bromine ions, because essentially they're just exchanging electrons, right, in a redox reaction here. And then Br2 liquid is going to react with the 2 chlorine ions, or produce the 2 chlorine ions. So they exchanged electrons to make that happen. Okay, that would be my net ionic equation, or what's really happening. It just means the sodium's just hanging out. Okay, one more. I'm not going to do this one for you. I want you to try this one on your own. So you need to first write the balanced equation, so make it balanced. Find your solubility like I did in green. Then anything that's aqueous, like I did in blue, you're going to separate into ions. And then the third part, like I did in pink, you're going to do the net ionic. So I want you to do this one by yourself and submit it with your notes. Submit with notes. I feel like I'm writing this so that you guys will actually do it. All right. So do that question on your own, submit it with your notes so I can look at it and see how you're doing.